Okay, eigenvalue problems. Numerical methods like initial value problems will quickly give you specific solutions to specific problems. And honestly, like whereas back in the day, you would need like a mainframe computer and send it via teletype or whatever mainframe punch card and get ticker tape answers back. Like now that the numerical methods have evolved to such a point that they're super easy and super fast to get a solution. The problem is that it will only give you a single solution to a specific problem. And sometimes that's nice, but sometimes you want all of the solutions to your problem. So that was the whole point behind assignment 7, question 2, where the trick is to non-dimensionalize your problem. And in doing so, you're going to get all of the solutions, regardless of what your radius is, regardless of what your thermal diffusivity is. That's the point behind that. Eigenfunction analysis is an eigenvalue analysis is another way that you can kind of get out that general behavior of your systems. And I'll try and show you guys how that works. Yeah. Do you guys remember what the general there's an extra V, value problem is? Yeah. Right? It's here, right? So the whole idea is that in this class to date, we've kind of avoided calling A an operator or like a linear transformation, but we kind of have to at this point, right? So the whole point is that you have a vector, you do something to it, which is linear, which means you have a matrix, and all you've done is just taken that vector and stretched it or compressed it. That's the idea behind the eigenvectors. There's a really great video from 3 Blue 1 Brown on the subject, and you can kind of go through. He gives like he's a real mathematician, right? So he gives you like the real mathematician explanation. I'm going to try and give you guys a different explanation, but before I do, I'm obliged to show you some examples here. So this is my cooked up function. Feel free to run it and play around with it. What this is it'll give you you can choose your elements for the 2-dimensional matrix, excuse me, the 2x2 matrix, right? And if you change some of these, right, you can see what's happening. So this is your original unit circle. It transforms into this. There are colors, so you can keep an eye on what's going on. If you do stuff like this, right? Because now you've done a rotation. You've done a rotation matrix, right? What that means, though, is that these values here haven't actually changed. They've just gone and stretched out in one direction. Sorry, this isn't a rotation matrix. This is just a skewing matrix, right? So these values have gone out and they've stretched in one dimension. This one has been compressed in another dimension, right? That ratio of compression and stretching are your eigenvalues, and these natural vectors are your eigenvectors. Excellent. You'll notice that these are orthogonal vectors. That is generally not the case. It is for symmetric matrices, and I'll show you another symmetric matrix in a second. If it's non-symmetric, then, well, that's not very clear. Right? You get the non-orthogonal system. This is a fair bit harder to imagine, in my personal opinion. But it is, of course, the general case. I forget, I don't think I actually tried this, but let's try this. If you put a negative. Yeah, okay, so this is wrong. It shouldn't be. The transformation is correct, but there is, in fact, another eigenfunction there. I think it's just because I'm multiplying the eigenfunction by the eigenvalue, and for some reason it's cutting off negatives. So I apologize for that. Just keep this positive for now. I'll try and correct that. Okay. With symmetric matrices, it is a little bit nicer because if A is symmetric, then it can be the Hessian of a quadratic function. If you guys remember, it's just a second derivative. And why that's nice is that now you can play around with it and see a little bit better visualization of what's happening here. So as you make one of these dimensions larger than the other ones, What you've done is you've taken your nice quadratic surface and you've made it into this valley, right? Why that's important? So the red line here is one of your eigenvectors. The green line is the other one. If you guys remember back in the day when we were talking about solving linear systems iteratively, we talked about this chatter. You can imagine starting at an initial guess here, you're trying to get down to the middle. But when you take a step, oh, you're on the other side of the valley. So you take another step and oh, you're on the other side of the valley again, other side, other side, other side. And that's really because you have this huge curvature in one dimension and this gentle curvature in the other dimension. Do you guys remember what this is called in the context of finite precision, or numerical methods, when you have a big difference between your eigenvectors, eigenvalues? Well, saddle point is this. I'll just show you. So that's the saddle point problem. Scale condition. Yeah, that's exactly it. So the condition number is really formally defined as the ratio of your highest and lowest eigenvalues. And this is why, right? It's literally because when you're trying to find these things, you get kind of lost looking for the minima here. There's also an analogy with the stiffness and the time stepping problem that we were talking about last week. It's the same idea. When you have different time scales, you also have different eigenfunctions here, eigenvalues in time, as well as space. So typically with stiff problems, you can even have stiff problems that are implicit method. Because if you have vastly different energies, you can have problems with that sort of thing. A good example for that is elasticity. Incompressible elasticity has a problem that as soon as you try and, like, normally if you displace a material property or a piece of material, you displace it a little bit, you get this restorative force, right? But if you try and displace everything around a circle together, then you get this huge restorative force because you're incompressible, effectively infinite. You get an infinite Hawking constant, right? That causes a lot of instability or stiffness in your problem. And the solution is actually to bust your pressure out, which is your spherical stress, as a separate variable. And in doing so, you give it a little bit of extra wiggle room, and all of a sudden your material properties can work a whole lot better. Your models can work a whole lot better. So, but it's because of your eigenvalues. I keep getting ahead of myself and dropping the my big revelation here. You can see that when you change the skewness of your matrix by adding in those cross terms, that's when your eigenfunctions are just kind of moving. It's not really a big surprise there. Okay, so I keep talking about eigenfunctions even though we're talking about eigenvectors. In the previous chapters, we spoke about how we represent solutions, right, as discretized as a vector. And then our differential equation becomes either a nonlinear operator. So this is, yeah. Right, so X is our solution. That's our actual answer. And then we have like a nonlinear operator, or we have some linear operator that's a matrix, right? And that's minus B equal to 0, right? Through finder, linear system, all fine, all good. The magic is that our vectors are representing functions. If we had an infinitely large basis to express our vectors, so if we mesh infinitely, right, we would have a continuous function. That's the definition of infinity, right? The fact that we're not, and that's called an infinite basis. And if you look into the literature, when they talk about eigenfunctions, they're talking about a function discretized as an infinite basis. But let's not bother with that because we're numerical. What that means is that your eigenvectors correspond to certain functions, right? So a lot of people will talk about these as eigenfunctions because that kind of is more in tune with what the physics is telling you. Sure.
So let's say we have this, right? That's solved. It's like one of the reasons why they use eigenvectors so that you don't have to take as much storage space and having a whole entire day if the eigenvalues are just insoluble. Because like, you know, ax equals lambda x or lambda x, like, and then you know that will equal b, like, or should we just keep on going?
So there are a few different answers to that question. In principle, no. Analytically, no. Analytically, you would need as many eigenvectors as rows in your matrix. Therefore, you haven't actually changed the problem.
Okay.
Realistically, if you could break out what those eigenvectors were, you could just take that as a preconditioner and transform your operator into a diagonal, where the diagonal elements are going to be your eigenvalues. Diagonals are trivial to solve.
Yeah.
So you'd be done, which would be ideal.
Yeah.
But that's more kind of like the numerical aspect of that. By the same token, if you can approximate what your eigenvalues are, you can also do that diagonal scaling. But now you're scaling by your eigenfunctions, by your eigenvalues. So you're changing that from like the elongated valley into something that's a lot easier for the systems. Again, with a conditional.
So basically, what it's doing is transforming that space into a different shape. I guess you could visualize.
Yeah, well, you're doing a coordinate transformation.
Yeah, yeah.
Effectively, and if you transform it into your eigenbasis, then it's diagonal. In which case, it's trivial.
Yeah.
The problem is that finding your eigenfunctions is more complicated than just taking it into GMRes. GMRes actually works by finding effectively the eigenfunctions, by the way. That is basically how it works. But that's kind of an advanced topic. Okay, the good news is that you guys already know all about eigenfunctions. This is one of those things that like your body knows about it and your mind knows about it, whether or not you know the mathematics behind it. Anybody ever swing on a swing? Right? Anybody like kick their feet when you're doing that? Did you notice what happens when you kick too fast or too slow? Right? Like, right? It doesn't work, right? But there is that natural frequency that if you kick in time, you have resonance and you get higher and higher and higher. Great. That is an expression. So that amplitude is the eigenfunction for that system, for the simple harmonic oscillator. And if you kick in time with that, then you're good. If you and by all means try this, right? Experimental practice here, guys, find a swing set and try and kick your feet twice as fast as you would normally want to. And you do actually end up getting a standing mode where your thing does hit another harmonic. You won't go anywhere because it's just it's a sine instead of a cos. But you will stand there and like the swing doesn't want to move that way, and you can't do that. In our last couple lectures, we were talking about PDEs and we were talking about like time steps, right? Those time stepping algorithms are our linear operators. They are how we take the system from one time step to the next time step. So in that context, eigenfunctions for that time stepping scheme is whatever doesn't change shape when you go from one time step to another time step. These are waves, right? That's the whole idea of the waves. When you swing your feet, you don't change your frequency of the oscillation, but you do change the amplitude. Right? So all you've done is you've taken your original wave motion and you've made it higher amplitude, i.e. you've changed its eigenvalue. That's it. Okay. As an example, coupled oscillator. So I put in, I'm going to go kind of quickly over a lot of this stuff because like I put this in and then I realized that this doesn't really illustrate what I was going for with the numerical method version of this. So I'm just going to kind of go through this quickly, and then I've got a lot of other math that I kind of need to go through, but I'll try and get through that quickly, and then we'll actually talk about real applications. Okay, coupled oscillator. Here, the whole point is that we have, I should have put in that picture. Okay, whatever. I'll find a picture and add it to it. No, that's the compound pendulum. And that one is an example of a chaotic system. Yeah, which is much cooler. So,
That's just 3 springs on a wall.
that one? Well, they're 2 blocks
Yeah.
connected by 3 springs.
Yeah.
Yeah. This is from the textbook. And like, if you wonder why you constantly keep getting questions that are all about like blocks connected with springs, it's because of this textbook. So this is the last textbook, the last textbook example where you have constants, blocks connected by springs. So the whole idea is now you have an acceleration, you don't have a static system. You have your spring constants, they're all the same spring constants. And you can write this out in terms of a matrix equation. You give it, okay, so before we do anything else, we can write this out as an initial value because we know how to do this then, right? We can know how to do the reduction of order. That's what this part is. We're defining our function value. We're giving it some spring constants. We don't actually have to because we can't actually non-dimensionalize that. You just grab all your terms, put them all together, and that's what we do later on. And then we solve and plot. And we get this mess. Right, so this is x1 is in the blue, x2 is in the orange. This is kind of the nice thing. I'm liking to actually finally use Jupyter interactive notebooks for what it's designed for. Right, what we can do is we can change the initial amplitude of the other one. Oops. Hey, what happened? Look at my sliders. Put them back. All right. See if this is gonna freak out again. Okay, there we go. Right. So if you change that amplitude, you can see eventually you get nice behavior. Everything nicely overlaps. Same on this side. If you go for -1, you get exactly opposite. There you go, right? So these turn out to be your eigensolutions. And basically everything in between turns out to be a combination of those, which is nice for things like signal analysis. And of course, as soon as people start talking about signal analysis, they start thinking about Fourier transforms. And again, because we now know numpy.fft works, we can just take a look at that one. Let me see if I can make this bigger. So what you see is as you go towards the same amplitude, you get this nice clean peaks, right? Because you've just got those two frequencies. Right? Unsurprisingly, there's a big connection between the simple harmonic oscillator and Fourier transforms in terms of eigenfunctions. That's pretty obvious. It's going to be. Okay. So let's take a look at dealing with this analytically. If we assume a phasor solution, because exponentials are nice for this sort of thing, they work out nicely. Specifically, this is what we get. Our acceleration is negative omega squared times x, times our original solution. This becomes, sure enough, an eigenvalue problem. Hooray! Here we can non-dimensionalize things completely, so we solve all the problems at the same time. The idea is that this equation has to have a trivial solution. It has to be degenerate. And the way that we make it degenerate is the way that we test for a singular solution, in which case we would never try and invert it, which is by doing the derivative. Excuse me, not derivative, determinant, right? If the determinant is 0, then the system is not invertible, right? Well, if the determinant is 0, then this is always equal to 0 for a particular x. Calculate the determinant. This is where I was writing this, and I'm thinking like this is more kind of like like differential equations or linear algebra, not so much numerical. So I'm going to go through this one quickly. Okay, so what you do, you put that in, you get the a polynomial out of this because that's what determinants do. And if you want, you can follow my SymPy expressions here. It's super simple. All I'm doing is just putting that together, having SymPy give out an expression at the end. And we get a quadratic. No surprise. Quadratic has 2 solutions. We can use polyval, or what is it? Polyroots in order to find all of the solutions at once. And we get our two solutions, 3 and 1. Great. We can try and find our eigenfunctions. And of course, we have a problem. Do you know what the problem is? Anybody? Kind of obvious when you think about it. We just found the eigenvalues as the system which makes A degenerate. And then we asked it to solve. So of course it can't solve because we just made a singular system. Why would it be able to solve? Yeah. So instead of trying to solve, we throw in our good old root finder. I think that's basically that's a whole take home of this class. Like use linear systems and root finder. Great. This is confirming, yes, we have found eigenvalues. Yes, these are the eigenvectors. And if we put it in here, what we find is that x1 has to be either equal or opposite magnitude to x2, which are our two eigenvectors. Okay. Do you guys remember how polynomial roots were calculated? And if not, start reviewing. The way that polyroots was determined is you end up making a companion matrix and find the eigenvalues of that matrix, which is kind of a roundabout way to do this, to find your characteristic polynomial and then use eigenfunction analysis to find your roots for that. So obviously we're doing something redundant here. The nice thing about this approach is that for small matrices, you can just use analytical formulae. They only go up to quintic, and only in special cases can you find an analytical formula for a quintic function, quintic polynomial. Otherwise, everything is just iterative. Okay, let's talk about numerical eigenvalue methods. In general, eigenvalues are easier to calculate than eigenvectors. It's to do with the fact that eigenvalues are actually an intrinsic part of the matrix, whereas eigenvectors are not. Eigenvectors depend on the basis that you're representing things in, whereas eigenvalues will always talk about the scaling between whatever that vector is and its new one. Okay. First of all, if you notice, this one will do. Take a look at what's happening to this vector here, right? Everything is stretching out along the longest vector. So there's the main iterative technique is something called Powers method. And the idea is that whatever the value is along that vector just gets stretched out. So if you just kept applying that function over and over and over again to this, you would keep getting more and more stretched out according to whatever that vector was. Really simple. Use this. And that's a good way to find the largest dominant eigenvalue. You literally just keep applying A over and over and over again to any vector, any random vector, and it will naturally arrive at whatever the dominant eigenvalue is. It does, however, feature matrix multiplication because you're doing A times A times A times A times A, which means accumulation of round-off error and computational expense, because matrix products are expensive. But it works. This is a random starting vector, and you keep doing more and more and more iterations, and sure enough, you align along the 1, -1 vector, which is what we wanted to find. Powers method is how Google works. Actually, their PageRank algorithm is they build a matrix of web interconnectivity, and they say whatever the strongest connection is the best answer. Well, guess what? The strongest connection turns out to be the dominant eigenvalue. So whenever you Google something, this is actually what it's doing behind the scenes. Or at least this is what it was doing behind the scenes back in the day that it was launched. I think it's evolved a little bit since then. But as far as I understand, it is still an eigenvalue problem. Smallest eigenvalue. Guess how we find that? Without looking at the screen. When you invert a matrix, you are inverting all of your eigenvalues, naturally. So when you're looking for the smallest one, it's super simple. All you have to do is take the inverse of your matrix and repeat the exact same algorithm. And then you get the smallest one. Problem is that at that point, you're inverting a matrix. And again, you have computational expense. So there are better ways to do this sort of thing. What's that? Why we want to do this. So a lot of people will already know, like you can kind of imagine why you would find your largest eigenvalue, because that's going to give you your biggest rate of change, right? Anybody have a guess why you would want your smallest eigenvalue? Without looking there. Yeah, well, what does that mean? Smallest slope?
Yeah.
Part of it. Your smallest rate of change, if you remember the von Neumann stability analysis that we use to figure out when the numerical methods are unstable, that von Neumann also applies to something like structures. So if you have a beam that's under compression and you want to know when it's going to buckle, what you want to know is the smallest frequency, which is going to be unstable. That is your smallest eigenvalue. And the corresponding eigenvector will give you that frequency. But as soon as that goes negative, your system is going to buckle. A big application for it. Condition number optimization. It's also related to the convexivity. I put that in because that's what the textbook says. I don't quite understand why the smallest one is related to convexivity as opposed to all of your other eigenvectors, because or all the other eigenvalues, because that's also your curvature. But apparently there it is. Get a question. Okay. A little bit abstractly, eigenvectors form your kind of ideal basis for these transformations. If you wanted to find your intermediate eigenvalues using Power's method, you can use a technique called deflation. And deflation removes that eigenvector from your operator. What that's like is taking a two-dimensional object and reducing one of its dimensions. So now all you've got is a line, and you just repeat the exact same algorithm and it'll find your next highest eigenvalue. But what that means is that your eigenvectors are the independent information quantities. If you have, and they're kind of like the fundamental ones. So if you think way back to the beginning when we talked about like linear independence between the rows of your matrix, right? The eigenvectors are the ones that are the simplest. And you can just remove them, the same as you would remove any other information, which doesn't necessarily make your matrix non-square. It just makes it degenerate. Now you have more dependent columns, things like that. It's a little bit more advanced than the sort of thing we talk about. Here's an example, and we iterate, and sure enough, we find the eigenvalue. Great. Okay. Any questions on those? These are algorithms that are kind of akin to Gaussian elimination when we talked about LU decomposition and solving linear systems. The take home for that one was that in some cases, those algorithms that are kind of like direct will give you good answers and quick answers. But if you remember, we did lots and lots of math, and then we figured out we can just treat A directly and do decompositions on it. The exact same is true here. So what that means is that we're going to make A into an easier form to solve. I'm going to skip a lot of this math. I'm just going to talk about it super high level. One of the main ways that you can do that is something called the Householder algorithm. What you end up doing is it's called a reflection algorithm. You take your zeros that aren't on the, when you take a set of zeros. So say you have blah, 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 and you want to zero out this element. Householder will give you a way to do that. And when you do that, then you just end up with a zero there. Why that's useful is you can take a series of these reflections and make your matrix into basically triangular form, right? And triangles are a simpler type of matrix. A lot of people will use this matrix. This particular matrix has a name, Hessenberg matrix. It only has one subdiagonal, right? Which is kind of like an abstract thing here, right? I don't want to get too much into what these algorithms are doing because it's like we don't even have an assignment on this stuff, so why would we? Why it's nice though is that you can use it to build. So nobody actually does householder except as part of another algorithm for something like QR decomposition. So QR decomposition is something kind of like LU, where we split it into the lower and upper triangles. This one is different. It's another one of these decompositions that splits it into Q, which is an orthogonal matrix, which means that its transpose is equal to its inverse. So already nice properties with that. And R, which is upper triangular. Why that's useful is that these guys are now much simpler to manipulate. QR can be used to find the eigenvalue algorithm. What you end up doing is you take your QR, you reverse the order of R and Q, and you keep applying that over and over and over again. And what you end up with is a matrix that's zeros on the lower triangular, and the diagonal elements end up being your eigenvalues. Problem with this one is that it's kind of complicated and has like matrix multiplication in there, but it's one of these techniques that are iteratively find these solutions. Some of the other techniques are going to use the householder reflection technique to make your matrix into a tridiagonal system, in which case you have the diagonal +1 and -1. Nice thing about that is that it's sparse. As soon as you have sparse matrices, you can throw other algorithms at them. Yeah. So that was a super high, super hand-wavy argument, but here we are anyway. SciPy methods will give you something called the eigen decomposition. It's pretty straightforward what's happening here. It's decomposing it, into there we go. Matrix V, whose columns are your eigenvectors. Matrix cap lambda, which is a diagonal matrix. The diagonal elements turn out to be your eigenvalues. And then V inverse over here. Why that's nice is that now you can use, these are basically your preconditioners, right? You use these as preconditioners and your problem becomes trivial to solve, which is super nice. And the fact that this is just the inverse over here means you bring that other matrix onto your other side of your problem and you can go off and do your thing as a preconditioner. There are a few different variants. I've just kind of made up a nice table here to kind of give you a high level overview of what they are. They vary based on the speed, the stability is a big thing, especially if you keep like doing the QR decomposition method, because no, QR is okay. Doing the powers method, you accumulate numerical error. And when you do the deflation, what ends up happening is that you propagate whatever error you had in one eigenvector to the next eigenvector, and you go worse and worse and worse. Householder algorithm, because of the way it's implemented, ends up canceling out your numerical error, your round off error, which has a nice property, but it's also computationally expensive. So we have different ones that are good for general matrices, symmetric / Hermitian. Do you guys remember what a Hermitian matrix is? Hermitian matrices are for complex valued matrices, and Hermitian is symmetric, but it's the convex complex conjugate on the other side. So all these still apply for complex matrices. Yeah. Oh yeah, all over the place. Yeah. Again, because anything that's like a wave operator, right, likes to be expressed in terms of phasors. And then you have that. Would you guys get the reference if I set phasors to stone? Yes. Right. So there are a few that will calculate the whole thing, the whole decomposition. Other ones will just give you the values because, again, that's generally faster to find. They are optimized for the symmetric permission cases. This one is an example where it's technically faster, but it's also a lot more unstable. So again, which one do you want? And then sparse matrices too. So pick your poison. They have a lot of different algorithms for finding it. For the sparse matrices, you generally want an iterative method and exploit that sparsity. There are also divide and conquer algorithms that parallelize better than others. Okay, let's actually do an algorithm and see why we're bothering to do any of this. And I apologize for not having this earlier. Let's look at the vibrational modes of a square member, right? So generally speaking, if you have a drum, does everybody know what a drum looks like when you smack it, right? Is that
Big drum, small drum?
all the drums?
All the drums.
Yeah, even a cup of water, man, or a cup of beer, cup of coffee, right? Same idea. It all looks like. Oops.
Yeah.
I'm just gonna cover over that. And hopefully it'll crap on recording.
But you can't see it, it's gone.
Ah, perfect. See what?
Yeah, exactly.
Right? You guys remember what this function is called? Radial coordinates? Bessel functions. Bessel functions are the eigenvalues of the Laplacian operator, which is that guy, on a circular domain. That is the cylindrically symmetric part. And what's really nice about that is that a lot of things in the universe are cylindrically symmetric, and you can use these things all over the place. There's also spherical harmonics are also eigenfunctions. Sine and cos are technically eigenfunctions, right, of any kind of vibration. But let's try it on a square or any other shape, right? I'm just using a square because square is nice. Anybody have any idea how we would go about doing this? How would you solve this equation? Subject to that boundary condition. That's how we solved it. How do we do it?
You got your grid.
Yeah.
And your boundary to do.
Got it.
Decide which method you want to get them inside.
Absolutely. We don't even need the time stepper, right? Flat out finite difference. You want to throw finite difference at this. You want to throw a finite element at this, whatever you want. This is an example where our unknown vector is actually the function. And our matrix operator that determines that whole finite difference nonsense is actually the operator that operates on it. Would it surprise you to realize that by doing the eigen decomposition of that operator, we're actually solving all the problems with the function, right? All of those functions can be expressed in terms of those things, right? This is how the electron orbitals are calculated too. It's the eigenfunctions. I had an example, but it was too much for me to put on. No, because it started talking about spherical. Way too much. Okay, so this whole thing should look very familiar, and if it doesn't, go back to the notes because we have an exam in a couple weeks. Right? All this is doing is creating the matrix that corresponds to the finite difference. And then, instead of solving it, we're going to throw H, which is the symmetric one. We should actually be throwing the sparse one at it, by the way, because it is a sparse system. And we can look at the eigenfunctions. So this one, not a big surprise. Things tend to vibrate in the middle. Not the only one. We can have these nice square ones that go off on the angle. Note that this isn't actually diagonal. The opposite is also true. The negative of these is just a matter of the eigenvalue, so that gives you the opposite side. And this other nice quadratic, quadrant, not quadratic, form. Right, and what this means is that all of your vibrations are going to be sums of these modes, which is kind of nice when you actually want to do real analysis of it.
It's giving flex speed. It means keep it this like flex speed.
I would be surprised if you did. Yeah. Did you do eigenfunction analysis
Yeah.
with FlexPD?
Well, we did modal analysis, which yeah.
Exactly the same thing. Yeah.
Yeah.
Yeah. Yeah. I think it's the mathematician definition versus the physics.
Yes, for vibration.
Yes. Yeah.
You would represent like the graphics sort of remind you of like cells splitting. So
Oh, I'm sure people have.
I'm sure it's complex, but
Yeah. I'm sure people have.
is it similar idea or is it sort of
I
found, right?
I haven't done biology in like 25 years, man.
Well, a cycle is a cycle, right?
A cycle is a cycle. Okay. I wanted to mention something else that's kind of neat here. There is a machine learning technique called, what is it? Model reduction. And the idea with that one is that you want to take a complicated problem and make it an easier problem to solve. One of the ways you can do that is called proper POD. I think it's proper orthogonal decomposition. And the idea there, you guys know how, like, if you have a signal, you do your Fourier transform. And that Fourier transform works because you have sines and coses. Sines and coses are eigenfunctions, and they are orthogonal. So what you can do is you can calculate what your signal is in terms of these eigenfunctions, your Fourier series. And then you can do magic on that. You can analyze the frequency spectrum, you can put it into solvers, you can get all kinds of things out of it. Turns out the same thing is true of these types of problems. So if you wanted to, I am still not a robot.
No.
Still, yet. If we were doing something like, I don't know, walking on a square platform, right? We're up in a building, we're on the roof, and it's a thin metal roof, and we want to make sure that the safety is there. We could build a general solution to the problem of all of us jumping up and down on this metal plate in terms of a limited eigenfunction, a limited number of eigenfunctions. It wouldn't be exact, but neither is a finite Fourier series. That is a method, and the nice part there is that if you have these functions as given, a priori, all you have to work out is the coefficients that go on with it. So you transform this massively, right? It would be like doing a Fourier analysis and only working out like 2 or 3 different modes. You can do the exact same thing here, which is pretty cool. Any questions? Okay. It kind of, so there are a few different uses for eigenvalue problems. Like the whole idea behind them is that you get you get information about your problem itself, not just the solution. So you can do things, right? You can do things like work out any kind of like frequency spectrum. For example, technically your frequency is an eigenvalue of a lot of these operators. That's why like Fourier transforms work, right? Yeah, it's very useful for that. It tells you about what's going on in your problem. So the example there was, and let's see if this is actually working. There you go. So this is an example of the T-Rex problem, right? Jurassic Park, you can see in the cup of water, all of a sudden you get the ripples on the surface. If you've never noticed it before, like next time you have a cup of something, liquid, obviously, like, and you jostle the table, you can see the surface vibrations, right? For a one-dimensional case, cylindrical symmetry, that's just a Bessel function, which are the eigenfunctions of Laplace operator on a surface of a liquid. For a square, that's going to be a lot more complicated, but they still do exist. So there are some examples, and I'd love to like get this equipment. What you do is you get a big sheet of metal, you put sand on it, and then you start knocking on it with a mallet, and it conforms. All the sand kind of like naturally aligns with, I think, the nodes for here. So if you did this, depending on your frequency, you would have all the sand kind of migrating out to the side. For this one, if you do it a little bit sharper, you're going to see it defining this line here because all the sand is basically being pushed off by the modes and it's collecting there. Right? And then even harder, and you're going to get this this nice quadrant pattern.
So you did that, like that same experiment?
How so?
Have sand.
Yes. Oh, yes. Yes. Yeah, absolutely. Absolutely. Wow. Okay. When I was like 6 or 7, so my parents are English. We went over to England and we saw, you guys know the London Eye, the big Ferris wheel, right? So I was with my uncle. He was a what was he? Metallurgical engineer. This guy like broke airplane wings for a living. That was how they did the safety assessment. And what I saw, so the Ferris wheel, London Eye, has like guy wires, right? Are you thinking that the cross pieces?
It's like, it's like, they're like
Yeah, yeah.
two legs, and then there's a wire.
Right. Exactly, right? So you've got this thing, and then you've got like the support wires down there, right? No big surprise there. But these wires had little pieces. Can't believe I'm quoting him like 30 years later. Right? Anybody know what those, so this is a cable that's, I don't know how big these things are, 100 meters. And then like somebody cut off like a half meter and just kind of stuck it on the side. Anybody know why? It is to cancel out resonance. That was not an accident. The idea is that if you just have a very long line, right? And you have wind, for example, wind in England, right? You could have constructive interference. And all of a sudden you could get, what's this called? Resonance in the cables. You design these little pieces to have a different eigenfrequency, right? So your resonance, right? You have it's harmonics. It's like playing a musical instrument. You have one that looks like that. That's one eigenfunction. Another one that looks like that. Another one that looks like that, right? This guy has a slightly different frequency that doesn't play nice with these guys. So when you do start to get these resonances, this guy tries to like tag along and just disrupts the whole thing. Right? You can imagine how important this is for building big buildings. Right? Especially like the windy ones and things like that. So that's where like eigenfrequency is. What's that? Any kind of like buckling. For example, stability analysis. We talked about von Neumann stability analysis, where like little numerical noise like kind of cascaded and had positive feedback to break it down. Same thing is true of like a pillar under load. And that turns out to be your stability is related to your smallest eigenvalue. So what that means is if you just poke it a little bit, if that eigenvalue is positive, it's going to reinforce and your pillar is going to buckle. Buckling is an eigenvalue stability problem. There is another nice one, which is called, and nobody has selected this topic yet, by the way, proper orthogonal decomposition, which is a fancy way of saying that so like with Fourier transforms, right? You decompose it into sines and coses, and you say that your answer is the sum of those sines and coses, right? That is generalizable. So this particular problem, you can say that any vibration on a square surface has to be a weighted sum of its eigenmodes, which means you no longer have to solve the full problem. All you have to do is work out what those coefficients are. So this is the model reduction technique called proper orthogonal decomposition. The orthogonal is if your eigenfunctions are orthogonal to each other, like sine and cos, right? You integrate over sines and coses and it's 0 for all cases unless n is equal to m, which is how you calculate these things in the first case, right? So that's another big field for that. Does that answer your question? Yeah. Okay. Think to Colmenares. Oh no, that one. Yeah. Yeah.
And then it just started going like this because all the pedestrians fell in step
Yeah.
and they almost took it down.
Yeah. I remember that one. Yeah. And then I think along the same lines as the pendulums, when you have the metronomes and like the 10 metronomes that are coupled. If they're coupled, then they all synchronize. Yeah, freaky. I think it was the Tacoma Narrows Bridge. Aeroelastic instability. That which is theoretically why we have or one of the reasons why we have the rings, right? So the wind was blowing over this bridge. It had a resonance and it blew the effing bridge down. Right? And the bridge is structurally sound, but the smallest eigenvalue was in the wrong direction. Yeah. Boeing aircraft. What's that? Did they actually not know about it, or did like all the engineers know about it? The management just kind of plugged their ears.
Did you guys hear that? 7,000%. 7,000% upsell on so
Private company gouging the military. Have you seen the American healthcare system? Pretty much. Any other big picture ideas? We've got 4 minutes left in this class. Otherwise, bring all your questions for tomorrow. If there's anything that hasn't quite jived, right? I'll try and come up with some practice questions, and we'll just talk about it like that. Shoot. Mhm.
Use AI to show that AI.
But just because something can create something else doesn't mean that it is something.
It will show how.
Pretty sure this is like the pretext of Terminator or something, no?
Yeah.
Like, okay. If you turn ChatGPT into Skynet, then all of the marks will effectively be moot anyway. So you can, but I don't think it would actually help your mark. Right? Well, there'll also be no failure.
Yeah, because it depends how you frame it, right? Not
And you don't have to worry about getting a job afterwards. Right?
you let that.
This is the project, guys, super open-ended.
Yeah.
Right? I showed you the metrics, the rubric or whatever you want to call it, right? Like everybody else in the room should walk away knowing when they might want to use it, how they would want to use it, and roughly the idea behind it. Other than that, give her. Any other questions?